or tube. So I fill it up. Let's say I put a barrier halfway up, and I fill the top barrier with water. So I got a positive amount of pressure, positive. And as soon as I open, and then I have a negative amount, there's none there. And these want to come together and reach an equilibrium. So if I take this out, boom, it will come back and balance up to an equilibrium. And that was the concept that Franklin really came up with. Before that, it was just, like I said, the vitreous and resonance charges are two, what we know now, positive and negative. One's positive, one's negative, and they have different attraction relationships towards each other and other things. And that was the extent of it. Franklin more or less came up with the concept of conduction and fluid flow. That basically it was an equilibrium idea and a conservation of energy idea, whereas the vitreous and whatever, it was as far as like it would annihilate each other, and that was it. There's no energy to deal with. But there was a conservation of energy here, and it would basically want to go back to its state of natural equilibrium or neutral charge. And what he speculated based on the spark that he saw was it appeared that the excess charge must be on the ball because it looks like the fluid flow of the spark is going from the ball to the finger. And it's important to note that if he would have been grounded, this is a symbol for ground. So it had a path to ground. This is insulated. And so that basically is the basis. That was the beginnings of electricity and electronics and, as a study, as a science, and also the eventual atomic model that we have today, which was a couple hundred years later, or almost a couple hundred years later. So, and let me see what else. There's so like I mentioned, so the plus charge, the excess charge, the fluid that flows. It was his theory was called a single fluid theory. Just as in the case of this glass of water, there's only one fluid that flows into the vacuum or the vacant or the negative amount which wants to be filled. And it's similar with electricity. That was the idea that Franklin more or less came up with. But the observation, funny enough, is that the fluid that actually flows, he was thinking it was the positive. That was his intention, just like the positive of fluid in the top of the glass filled the void down here. Well, this would have the positive flow. This would be what flows because what he observed on the spark. But we know now that it's actually the other way around. It's the negative charge that's flowing to the ball. And that can be explained why Franklin saw it that way. I can draw a little bigger representation. Here's the fingertip. What happens is when you bring a negative, two different fields together and they want to attract each other, you get a development, if it's strong enough, development around the atmosphere of negatively charged particles around the negative end. And then you get a field around the atmosphere of positively charged particles. And as this field gets stronger and they get closer together, the two fields will touch. And right at that moment, there's no real path really to go until they both touch each other, and that creates a channel. And then what happens is that, bam, this channel is created, and a flash of light goes from it's a little distance from the negative charge, and that's what's the confusing part. And it happens instantaneously, and you'll have these branches too. And it appears as the excess charge is coming from this body and going to that body. But in actuality, what's happening is that you got this invisible field up here. It doesn't show any light until after the channel is open and a spark happens and it instantaneously shows a flash on this end. And even since there's this gap here, it kind of looks like it appears as though the charge is coming off that body. So that's where Franklin got all the concepts, everything right, except which actual fluid does the flowing. But it all comes out in the wash, more or less. You can think of it doesn't really matter which one flows. If you say you have two positive charges that are equal, if you do this, it's like algebra. If you do the same thing on both sides, so multiply it by a negative on both sides. If you're doing the same thing on both sides of the equation, they're still going to be equal. It works out in the wash is basically what I'm saying. Now, we talked about charges, things like like charges repel each other, unlike charges attract each other at a certain force, or 6.25s times 10 to the 18 negative electric charges for a clump or unit charge as it works out in math. What other important things to point out? Well, how do we create this charge difference? So there's different ways to create this, but different in charge, absence and an excess of charge. And it can be the main ways. The ones I want to focus on more or less are by friction, I think it's called the triboelectric effect, it's called. And then there's by chemical reaction, you can create this difference, this electric charge body difference. And then you can also do it by sunlight on a material, special material, semiconductor. So the friction way was the one we're most familiar with. It's the most natural way. Like if you comb your hair with a rubber brush, and that would be similar to the amber, let's say, and it's combing in your hair is the fur, and you provide a charge on a rubber brush or amber. It would be resin-like, and you take it to pieces of paper, and it would attract a piece of the paper because it would have two different charges, and unlike charges attract. So that's pretty much the first way that was focused on, and it was actually observed. We already pretty much covered friction, the rubbing. Basically what you're doing is that one material is rubbing the electrons off another material, giving that material a positive charge, and the material that's rubbing electrons from it a negative charge. So that's what friction's called. There's the other method, which is a battery, and that was discovered, let's say friction was focused on during the late 1700s, and right at 1800, a guy named Voltaire came up with the voltaic cell, and that was revolutionary. It was revolutionary because prior to that, let's say we have a graph here. This is a graph over time, as time passes, and prior to touching the two charged bodies so they can reach equilibrium, you have a high potential at this point. And as soon as you touch them, bam, it drops down dramatic, quick, like a spark. Fast as a spark drops, that's how fast it drops. So you really can harness a whole lot of that in a lot of different ways. What Voltaire came up with was a battery. And if you were to draw a similar graph over time, what the battery provides is a consistent steady state called DC, direct current voltage, over time, indefinitely, until the process runs out of energy. And that process basically, say we can explain it this way. If we have a container with what's called electrolyte, it could be fluid or it can be dry, and we have two different metals in that, what's called the electrolyte, and that has a special chemical reaction with each of the two different pieces of the metal in such a way that the chemical reaction with one metal leaves that metal with a net positive charge, and the other metal, it reacts in a way that it leaves that metal with a net negative charge. And if you were to provide a path, in this case, we'll talk about this more later, but if it was a straight wire, you could get steady state current until the wire burnt or the battery blew up or something. But normally you have something with what's called resistance. In other words, it has a resistance to the flow, so you don't get the super fast flow. So it slows down the flow, and it's called a load. So if you were to put a load in between the two terminals, you would get a conventional current. Like I said, in actuality, it's the electrons that flow, but for math purposes, and since he started out with the plus, being the wrong fluid, it works out better mathematically if we treat this as if the current is going this way. To clarify things, current is symbolized with a letter I, and it's in what's called units of amps. And then here, we'll get more detail of that later. They call this voltage, or the force, or the pressure, if you will. And that's in units of volts. These things, as far as a timeline, before I go into sunlight, because I'm going to start talking about the atomic theory, I haven't really talked about the atomic theory because all this stuff was analyzed and explained back then in this manner before the atom was actually known, or the model was known. Prior to that, it was basically clumps of different charges, not a nucleus atom with electrons swirling around, and that most of the weight resides in the positively charged proton. That stuff wasn't figured out until about over 150 years later. So it gets confusing. So before I go into, and my next topic is how to generate a voltage with sunlight, and that more or less requires the atomic theory, more or less. There's a twist on it that's interesting. And so before I start talking about that, I'm just going to go through a brief history of the chronological events of how things came about in the study of electricity during the 1700s and 1800s. Just so you can see that when it's normally taught, and it can't be taught chronologically in an effective way, but it gets a little confusing because the order that you get taught things is not chronological in history. So I figured it might be worthwhile just giving a brief sketch and talking about what I call the unit men. That's where all the units were made. Like I just mentioned, this is called amps, but that wasn't called amps until quite a bit later. So all these things kind of came together in different orders, and it gets taught in different orders. So that'll be the next class or the course. That's it.